All right. Thank you all for coming. Really happy to see so many here. I was a bit concerned about doing a compiler talk at the end of day 2, but you must be the really hardcore of the hardcore. My name is Martin Skarsaune. That might seem like a difficult name. That's because I'm from Norway. And I work for a company called Cantega, a small consultancy company, working for different clients. So compilers is not really something that I do in my day-to-day job. So that's sort of the message, that it's not really that difficult. And at least for me, it's been very rewarding. I learned a lot from looking into this, so I hope you will feel the same way. So when we're going to learn something new, it's good to have a concrete example and something we want to achieve. And today that will be implementing goto statements in Java to be able to write proper spaghetti code. I don't know how many went to the 20 years of Java talk yesterday, but today we'll sort of break down everything in just 1 hour. So what we want to achieve is this. We want to introduce a new syntax to the language. So we use the keyword goto and then an identifier that should identify a label statements, and then we terminate the statement. And if you're not aware of the goto at runtime, what the goto should do is that the program control should then move to that target statement. And since we're looking at the compiler, it's good that the tool also gives us some useful feedback. So we want to verify that the label that we attempt to jump to is actually present. If not, we should give a compilation error. We also want to analyze the flow a bit to see if we can warn the developer that there could be an indefinite loop here. And how we're going to achieve it. The OpenJDK is an open source reference implementation of Java. And as a part of that, you have the implementation of the compiler. And as you will see, that is written in plain Java, and it's quite understandable code, really. So what we will do is we will modify the source code in order to make it support gotos. And at the end, we want to run this little snippet here to print out some code using gotos. But before we set out, I guess some words of cautions are advised. Setting out into this dangerous territory. Dijkstra had an opinion about it. So in 1968, he felt that he had to write a letter to the editor about the detrimental effects of goto programming. And he even states that the quality of programmers is a decreasing function of the density of goto statements in programs they produce. And it doesn't detail the exact function, but if we take a very simple percentage distribution, and you take the amount of gotos divided by the total number of lines of code, I think today we'll maybe reach 30-40%. So my quality as a programmer will then decrease by the same amount. Luckily, we have quite good employee protection in Norway, so I expect to have a job when I go back. If we look at the very basics, what is the compiler? It's basically a converter from one format to another. And in computing, that means normally some sort of source code and then some executable code or targeted at some instruction set in the other end. Whereas in Java, it would then be Java source code as the input and then Java bytecode in class files as the output. Very common design for compilers is to distinguish between front end. So the front end is what deals with the specifics of that programming language, rules, and so on. And the back end is then more geared towards the optimizations and logic and for a certain target platform. So if you're doing a native compiler, this is fairly obvious, that you could have the same programming language and then target different architectures to decouple these things. When we look at the Java compiler, taking this even further, it's more like a pipeline. So I have this ribbon at the top, which we will use when we go through the various phases. And I also see some source code that I cut out below there, which basically is that one phase has an output, which then becomes the input to the next phase. So if we start at the beginning, we have the so-called parsing. And we divide this again into two parts. So the first part is often called scanning or lexing. So we see we have our syntax here. We want to support the syntax goto, some identifier, and then a semicolon. And what the scanning does is you have this sequence of characters that make up your program. And the scanning will then turn this into some higher level structures. So you don't need to do string comparisons everywhere. Symbolic representation of the various pieces of source code. So for instance, the goto keyword should make up a goto token. The identifier should be an identifier token. And a semicolon should be a semi. And if you went to the 20 years of Java talk yesterday, you would know that goto is already a reserved word in Java. I guess they thought it was a good idea to keep it for a rainy day. So the thing is, what we do today will not break any existing Java code, because no one has ever written a Java program with gotos. But we will give a very good way to break new code. And also the implementation, the way they implemented this is that actually there's already defined a token for it. So if we run a little test, we instantiate a scanner on that piece of code you just saw. It's not the Java util scanner. It's a scanner within the compiler package. You can then tell the scanner to proceed to the next token, verify that it is a goto token, go to the next token, verify that that's an identifier, valid identifier, and then look at the third, that is a semi. A very important concept in all compilers is the abstract syntax tree. So we saw first we had the characters, which made up tokens, and the tokens also keep reference back to the location in the string, so that when the compiler gives you errors, it knows where it came from. And then on top of that, you have the syntax tree. So this is a sort of simplified figure. And the word abstract means that it should be sort of decoupled from too much specifics of a programming language. And you probably, if you program in Java or any other programming language, you would recognize the concepts you see here. You have a compilation unit, that's normally a source file. You have one or more classes. You may have some fields, you may have some methods. Methods have signature, body. Within the body, you will have then different sorts of statements and expressions. And this structure can be quite large and complex. And to deal with that, you will see that the compiler is largely based on the visitor design pattern. So we have specific typed nodes for these parts of the syntax tree, and then you will have then typed callbacks for each kind of node. And this makes our job a lot easier, because we don't need to tackle the whole structure. We don't need to understand everything in there. So what we will do today will be relate to gotos and not much else. But since goto is, you can then make changes to the compiler without creating new kinds of nodes. But today we're doing something completely new in Java, which means we have to create some new types for that. For these nodes, there's both an interface hierarchy and a class hierarchy. So we create one of each of those. And then there are all these visitors. And since the visitors are type-based, we also need then to put in quite a lot of boilerplates to support these new types. I won't show all of them, just a few ones that are interesting. For instance, there's a visitor called pretty, and what pretty does is to print the parse tree back into Java, which is very convenient when you're debugging. You just place the cursor on and know that it will show it like Java structure, which is source code we were used to reading, so therefore that works well. And two of the visitors that are mandatory are attribution and generation, which we'll come back to, which we have to override unless we'll get a runtime error. And then within a scope, a block, there will be some goto statements, and there will be label statements that will be the targets. And therefore we have this helper object that helps us keep track of them. It makes the code and this presentation a bit easier. So you basically have relations from gotos to identifiers and from identifiers to targets. And we keep track of the sequence so we can traverse these relations in any way we like. So now we have created the new nodes and the boilerplate needed for it. So it's time to start using it. And within the parser, there is a method called parse statement with a long switch statement. So we add a new case for this this new symbol, and we go to the next token. We require it to be an identifier. You will get the compilation error if it's not. Then there's some code that's a little bit hard to read, but it's basically calling a factory that again calls the constructor of this new node. And then we require the next token to be a semicolon, and we return it back into the tree. So we can stop a little bit here and take a look at. So if we run all the tests without making any changes, so this is the original Java compiler. We'll see we get a lot of parsing errors. So then if we load this code that we includes the parsing functionality, we can run them again. And we will see that we don't get the compilation errors. And there are some, we will get back to the particular ones here. We don't get a compilation error for the missing label, thing I'll show later. We don't detect circular gotos. But for the success case, the code now does compile, and it does run. So the only problem is that it does not do what it's supposed to. We don't get the output we require. But from now on, the nodes are known to the compiler, and they're accepted, just that we don't do anything with them yet. So if we come back to the process here, so there we're pretty much done with the parsing. Let me bring that up in presentation mode. Yes. The next phase is called enter trees. That is it's quite high-level sanity testing of the compilation unit as such. Checks things such as file names and folder for package and class names, whether the class is already defined. And as you will see as we go along, most of these phases do some corrections, but they also they do some tests and very sanity testing, but they also do some minor corrections. So for instance here, if you have a Java class, you've not declared any constructor for it, you know you will get a default constructor, and that is then inserted by the compiler at this point. And then we enter the process phase, which means process annotations. If you recall, when annotations came in Java 1.5, they were suitable for third parties to use and generate code, verify stuff, and so on. And ever since Java 1.6, the processing of annotation has been part of the normal Java compilation process. And there's a plugin API for that. It's also some relevant command line switches here, because by default, the compiler will both do the ordinary compilation from Java to class file, but if there are any annotation processors, it will also process them, so it could be more than one output of the process. So if you only want to produce the class file and ignore any annotation processors, you can use proc none, or you can use proc only if you don't want to compile Java code, just to do some annotation stuff. Some colleagues of mine have a project where they actually use this, and it was quite easy to get started with. They have this configuration injection thing where they there's an underlying requirement that whatever configuration you inject should either be a string or a primitive value. So we see an example here. We inject a string, which is OK. We inject an int, which is also OK. And then we attempt to do it for an array, which is not OK. So this would give you a runtime error. But with a annotation processor, we can detect this as compile time, so you won't make that mistake at runtime. So there's a particular file that you need to add and declare your processors. And I've simplified here a bit, but when you have a processor, you basically say what kind of annotation it deals with and the source version. So you see towards the bottom here, we check for the type of that field to be either a primitive or a string. And if that is not the case, we give a compilation error, so your code will not compile if that is the case. And it's simple as that. You just add it to your class path at compilation time, and that's all there is to it. At Devox last year in Belgium, there was a presentation by Google. It's on Parlays, and if you Google the session title, you can find some resources. My presentation is already on SlideShare, so any references you can get from there, because Google uses this for a lot of stuff, and dependency injection and so on. And if you want to do something with the compiler, this is probably the easiest way to start. It's quite straightforward. Then after that, we reached the attribution phase. And this is where the bulk of the tests, sanity tests, take place. So we have semantic checks for type compatibility. If you reference method, reference fields, reference variables, it checks that those are OK. And again, it does some minor corrections, like adding calls to superconstructor. So what's valid in our case? Well, we said that if you attempted to do a goto to something that's not there, we would like to detect that. And the way we do that is this one visitor that I said was mandatory, the attr of attribution. We get a callback for each goto. In the goto class, we have a way through this helper object to find the target in our scope. If it's not there, we give a compilation error. Here we can reuse the compilation error that's used for a continue and break. You can break auto loops. That's why you have labeled statements in Java, which is what we reuse now. I think I will skip the demo of each part, and we can look at the end result. So that's for the attribution phase. Next phase, so attribution was more like static checking of things. The flow is dealing more with the flow of your code. For instance, do you have unreachable code, or have your variables been assigned a value before you use them? Is there a proper return from your method? if you have final or in Java 8 effectively final variables, have you tried to assign to them more than once? And also follows checked exceptions, try, catch, throws, and so on, to see that that makes sense. So in our case, we said we wanted to detect if there is a circular goto, a potential indefinite loop here. And then there's a visitor for that as well, that we override. And we have this method in the helper object that uses the knowledge of the sequence and the relations to traverse them and see if it ever comes back to the same position. And since if you're crazy enough to use goto, you probably don't want an error in this case, so you'll have a warning then instead. And since this is something new, we simply add a new compiler warning to the properties. I think we can skip that as well. So now we come into the more useful stuff of today's presentation. Because when I did this, and I mean, as with any piece of software, the compiler, which we rely on so much, is often a good idea to have a look inside. And at least for me, a lot of things fell a bit into place when I started. I mean, you can read articles which explains you how it works, but if you follow it step by step from the inside, that at least was quite revealing for me. So the most interesting part I find is the desugar phase. So desugar has with taking out sugar. So you have the syntactic sugar in Java, which allows you to express certain things in an easy way, which is then realized with lower level constructs, and it's the job of the compiler to do that job for you. Yeah. So, for instance, when generics came, it was decided that generics should be backwards compatible, so that at runtime, generics don't really have any effect on the VM, but it should be checked at compilation time. So, for instance, the comparator interface was then made a generic interface with the type parameter. So you should declare, perhaps a bit silly to create a comparator for integers, but if you wanted a comparator for integers, it should then have an integer type parameter, and your compare method would then have to be implemented with integer parameters. The problem is that when we have type erasure, it's still a comparator as before, but now we have a compare method here with integer parameters, and the compare method should have object parameters. Does anybody know what the compiler does in this case? Have you seen traces of this?
It raises specific type information.
Yes. Yes. But in addition, in order to make this work, yeah, bridge method. So it will add this synthetic method, which is called a bridge method. Synthetic is a flag to say that this is something that the compiler created. So it will then create a compare method with object parameters, which then makes typecast and calls your compare method. And you might have seen traces of this in your work. For instance, we see at the top here, all of a sudden there's a stack frame compare object, which we don't have source code for. We see that it thinks that it's on line number 1, which is an import statement, so that doesn't really make sense. And you also see it in the stack trace here. So this is an example of a bridge method. Maybe sometimes if you're debugging and stepping, you will encounter these sort of meaningless frames. You can also filter out usually synthetic methods when you debug. Then we have inner classes. In Java, you're able to declare one class within another. And so here we have an outer class with a private foo method. We have an inner class that implements runnable and calls foo. And so what happens? So when I saw desugar, we saw a trans types, which is types erasure. Now we look a little bit at lower, which is more like really about taking out syntactic sugar. We will look a little bit at lambdas towards the end specifically. So what happens is, and you've probably seen this on your disk and when you're running programs, that this inner class is then extracted as a separate class. It will have a reference to the outer class and a constructor to set up that reference. And in the place of the location where the inner class was previously, we instead get a call to a constructor of this new class. The only problem is, and the run calls run the foo. The only problem is that now this class is just another class in the same package, and you have the foo method, which is private in the outer class, so it's not visible anymore. Does anybody have any idea what the compiler does here?
Reflection.
No. Fortunately not. What you will get is what's called an accessor method. So the inner class will then call the static accessor method, which in turn will then call the foo. So you may also, I thought I had an example of that, but you may also encounter these while you're debugging, that you get these access methods out of somewhere. Then we have more syntactic sugar. So I have a tiny snippet here which uses quite a lot of that. We see we have a the arrays as list is a generic method, and you use type parameters, so they have to be objects. What we see in the source code is just plain ints, and so the compiler will then box them. This is the auto boxing, so it will box these integers to make them proper objects. And inversely, we have an integer, which you see we use in the calculation further down, which is also not possible. So here we will unbox it back. And then we see this method here, asList, is a var args, so you can use 0 or more arguments when you call it. But at runtime, there's no such thing as a var args. So what the compiler does is then to set up an array to capture all these arguments and pass into the method. We also see there's a for loop here. This was also introduced Java 1.5. As you know, the for loop can either be used on arrays or instances of iterable. And the requirement for an iterable is that it should provide an iterator. So here the compiler will move the iteration variable inside the loop. We'll then do a synthetic variable for the iterator, make a condition check on availability of next item, and then assign that into here. So all of this is work that the compiler does for you. Then a very nice feature in Java is the enums. You can have a set of possible values represented in a type-safe manner. And you have probably experienced that we can use this very compact syntax here. But that when you use these objects and this class, there's a lot of built-in functionality. The thing is that the compiler has to create the specific functionality for this. So it will create a constructor with a name and an ordinal for each. That constructor will then also be invoked. I just left it out to save some place here to create proper objects of this class. We get the value of, and we get the values generated for each enum. And one very nice thing about enums is that you're able to use them in switch statements. And Java as a language only supports primitives in switches. So how is this possible? When we look at what the compiler does, there's some rather confusing stuff going on here. It generates a helper class for this switch statement here. It will declare a sort of lookup integer array with place enough for all the values of this enum. So it's initialized to zeros. And then we see in our case we used the value maybe. So it will then, in a static block, set up that in the ordinal position for maybe. It puts in the number 1. And then this relation here then, from the switch statement, we can go through this lookup and use this value in a case. Does anybody have any idea why the compiler goes through all this problem? Can it just use the ordinal directly? Yeah?
So if you change the enum, it doesn't break existing code?
Yeah, exactly. Because this static block will run every time. So if you change the enum, you don't need to recompile this piece of code because it will always work. So it's yes. So that's more or less what I had on dsugar. Now we get into the real stuff, the generation. Yeah, the generation does some things. We organize the initializers, tidy up a bit. A string concatenation. The initializers are done on the parse tree. Well, as you will see, the string concatenation is actually done directly into the bytecode. But most importantly, this is where we produce our bytecode for our program. So if you have a class here with a field initialization, we have a constructor that is gradually then combined into one method. And actually, as you maybe seen when debugging other things, it's actually called init. So it's at there's really no such concept as constructor at this level. Same on for statics. You have a static initializer, static block organized together, and that's the CL init. As string concatenations, we can use the plus operator in Java. But there's really no such operator. So what the compiler does in this case is to instantiate the string builder and then append the various components and finally make a string out of it. So in our example, we want to then make this gotos do something. And there is actually a bytecode for doing jumps already. It's already called goto. So the bytecode is goto, and then you set an address that it should go to a bytecode index. But the problem here is that we now attempt to do something, use something for which it was not designed to do. That is both on the bytecode level and even more on the actual implementation of the compiler. So since now we're bending things quite a bit and we're hacking it up a bit to make it do what we want. So this is the normal use of a goto. So we need to understand a little bit of bytecode for this. So here we have a branch, or we have a conditional with 2 branches, sorry. And the way that this is represented in bytecode is we have a conditional jump for the if. This is if equals. There are variants of conditional jumps. Then the compiler starts to insert the code for the else branch. And then the goto is then used for an unconditional jump out of the else branch to whatever code comes after. And at this point, there's a helper class called cold. It's marked as not alive because, as for an optimization, if the if branch is dead, we don't really need to do a goto. Then execution could just follow. And also, this goto is added to a list of pending jumps because we do not yet know the location. And now we enter the if block. And since Java 1.5, there's a requirement that the target of any jump, you must have something called a stack map to help the verifier, bytecode verifier. So now we have the if block, and now we can patch up the conditional jump here. And again, for the code after, we'll do a stack map, and now we can patch the goto. So this is sort of what we have to fight a little bit with, since we're doing something which is not really meant to do. So for our gotos, there are two scenarios. One is the label is already declared, and then we encounter a goto. We know through this helper object whether the label is used. If it's used, we must have a stack map. Then we know the position of the code. And when we later come to the goto, we can then patch it immediately because we know the location. And in the other case, if we're jumping to a label that we don't know the location of yet, we must emit a goto, add it to the list of pending, and turn generation on again. And then we can patch it. If you don't get all the details here, it's not important. Now we're diving really deep, but just to show why it was not as straightforward as you would think to do it. Yes. So again, the implementation. There's one of the visitors, the mandatory ones, was the gen, which is used for code generation. We modify it for label statements and add implementation for goto. So for label statements, if it's the target of this new jump, we'll put the stack map in front. And for the goto, we add a branch, and there's some logic here to either patch it immediately or keep a reference so that we can resolve it later. So now let's see if we can get this to run. My knowledge is probably the first time on the British Isles that we see gotos in Java. Yes, so I included all the fixes also for the. We could look at them one by one, but I guess the most fun part is to debug this stuff. Could perhaps. Yeah, so you see now where the code is. For step line by line, we come to 2, and then we encounter a goto, go to 4, and woo, and up to 4. Oops. Go to 3, 5. Go to Devox UK. That's it. And we can see also the other tests we had here. For the circular warning, we ensure that we get a warning for the missing label. We want the compilation to fail, and we want a certain error string, and the success should compile, it should run, and it should do as it's told. So spoil the surprise there. So we seem to have reached our objective. Perhaps we got into more problems than when we started out, but step 1 is done. Finally, I would like to have a little bit look at the lambdas in how they're solved in the compiler. I find the solution to lambdas in Java very fascinating. Many interesting solutions they found there to add this to the language. Because the lambda is several things. It's to change the language, new syntax. It also has a lot of implications for the compiler, and but also quite a lot of the work is deferred until runtime. And I will provide some references to some articles at the end. As if, oops. Thank you, Microsoft. Oh. Yes, let's see if we're luckier this time. Yes, we have a trivial lambda here. So I think we lost a minute there, so we just have to proceed. So you may have seen, if you're looking into the class files or debugging, that in this case, this is an improvement over inner classes, because here the Lambda implementation can be static, because we don't have any requirement on the state of the enclosing object. The name is generated based on the location in which method, and the Lambda parameters are copied into this method, and the body is then also. But at runtime, there is a requirement that there should be a comparator. So in Java, lambdas always have to have a functional interface as required type. There's an invoke dynamic call, so I try to sort of make source code to represent that. And that call to the Lambda meta factory then contains some static information about the role that this Lambda should fulfill. So we have things like the method name, the type, and the method signature. We also have a reference to the implementation and the signature of that. And if you use reflection and to introspect this Lambda instance, you'll see something like this: generated name, but with that method and implementing the correct interface. And the way this works, so I said the invoke dynamic, the bytecode, and contains this meta information. So at runtime, when the Lambda meta factory receives this call, we have the actual implementation is then based on the inner class. So we have inner class Lambda meta factory. They use a framework called ASM, bytecode generation framework, and produces a Lambda class. And in this case, it will even reuse the instance from time to for each call, so it was static. And the reason they did this was that, okay, this inner class works fine, but perhaps in the future versions of Java will have even more optimal implementations of lambdas. So it's deferred then until runtime. So maybe at some later version of Java, you can still run this class file with the current invoke dynamic call, which will then maybe do something even smarter. And that is even the case if you serialize the instance of a lambda. So we have a lambda instance, and we serialize it. And then it's not that actual instance that's being serialized. It's the same information that was in the bytecode is then serialized in sort of neutral fashion. And then if this is attempted to be deserialized, we go through almost the same process. So it takes this static information and creates an object that fulfills this. So the question is, okay, that's great for Java 8, but what if you're working on some old WebSphere or something? Is there any hope of solving this in another way? Well, we could do something about capturing the bytecode of the generated class, but since we're looking at the compiler, could we resolve this at compile time instead? So the first thing we do is there's a file called source Java, which deals with what functions are supported in a certain version. So we say that, okay, anything newer than 1.5, and then since we need to hack some stuff here, I add another tester to see whether we need some special handling. So if it's earlier than 1.8, we'll do that. And in the place where this invoke dynamic call is inserted, instead I have a new helper class that implements it on the fly, and we get this class generated as part of the compilation cycle. So this is slightly different naming, and we also see that we get the bridge method in this case, so we rely on other logic in the compiler for that. And when we invoke it, instead of invoke dynamic, it's simply a constructor call. So if we attempt to see if we're able to make that run. Let's see. So if you run it in a normal fashion with Java 1.8, I'm running a couple of lambdas, storing the value using reflection to pull out the details. But if I wanted to do Java 1.6, I will invoke this modified compiler with some command line arguments to make it suitable for that, and run it in Java 1.6 instead. So here we see the Java version 1.6. I could even just compare the two. See, the result is more or less the same. We get additional bridge methods in 1.6, and the naming is slightly different. But apart from that, at runtime, it's more or less the same. So just shows you because all this information is hopeless software. Yeah, let's head here. So to wrap up, compiler is written in plain old Java. The compilation occurs in phases. Advances in the programming language, such as Syntactic Sugar, required very much effort and good support in the compiler. And lambdas are compiled in a forward-compatible manner, but it's also we could do it in another way. Yeah, the basis of this is the OpenJDK. There's also a more step-by-step compiler hacking tutorial available if you want to try it yourself. It's probably easier to follow some simple examples there. Article by Brian Guts about the decisions in the Lambda translation, some sample code that I ran today, and this slide pack is already on SlideShare. It's time for questions. Let me see. We were told to test out this new solution. Yes, how to write a test that checks that your code doesn't compile for when you go to label is missing. I have a test for that. It's based on, if we have the tree here, I should then. I created a helper class that basically does two things. It first compiles the code and then tries to run the code, and just checks the exit value of it. So for the missing label, I expect this error to occur, and I also expect the compilation failure. So this is just testing that the return value is not 0. Yeah. Any old-fashioned questions from the audience? Yes?
How many lines of code, more or less, did you have to add or modify?
That's a good question. I would. The last time I did it, I had the number ready. I think the boilerplate stuff, setting up the visitors and that, was like 300 lines, and then the rest was maybe 100. I can check it up later. It could be wrong, but it was more boilerplate than actual changes, really.
But it was also because it was already a keyword.
Yes, that of course helps, but it wouldn't be that difficult because the tokens are just defined in a list. So you just say which characters you want and add it to certain places. Yeah. Well, if that's it, I would thank you for your patience.